This video is on pH and neutralization. We will talk about pH, I'll define it and talk about the scale. I'll then talk about how to make some calculations involving pH, and then we will talk about neutralization reactions and acid-base stoichiometry. All right, so what is pH? Because you've probably heard the word or the term pH. pH actually stands for power of hydrogen, and it's a measure of the concentration of hydrogen ions in a solution. Remember, you can abbreviate the concentration of something by putting it in brackets. It happens to be based on a negative logarithmic scale, that's log base 10. So on your calculator, you have a little button that says LOG. You're going to be using that button. So because it's based on a negative logarithmic scale, whenever you come across something that has a low pH, that means it's got a higher concentration of hydrogen ions. And if you come across something with a high pH, that means it has a lower concentration of hydrogen ions. So it's kind of the opposite of what you might expect, since, hydrogen ions are a measure of something that's acidic or basic. If it's a low pH, that means it's got greater hydrogen ion concentration and is also more acidic. And something with a high pH or a lower hydrogen ion concentration is less acidic, more basic. So you can calculate the pH of a solution if you know the concentration of hydrogen ions using this equation. So pH is equal to the negative log of the concentration of your hydrogen ions. So for example, I might ask you to calculate the pH of a solution of, say, lemon juice. And I know that its hydrogen ion concentration is 7.9 times 10 to the negative third. So what I would do is I would go to my handy dandy calculator and I would locate this button, the logarithm button. And I would enter into my calculator negative and then log, hit the log button, and then 7.9 times 10 to the negative 3. And then I'd hit equal, and that would tell me that my pH is 2.1. And remember what I told you, that low pHs have a higher hydrogen ion concentration, and 2.1 is a pretty low pH. You can always estimate the pH of something without actually making a calculation by just looking at the exponent. If you take the negative off the exponent, that will give you a good estimation of the pH. So if I were estimating the pH of lemon juice, I know it's going to be somewhere around 3. Now, 2.1 is not exactly 3, but it's not far off. So let's try a second example. You try this one. So I want to know the pH of swimming pool water if the hydrogen ion concentration is 2.5 times 10 to the negative 8 molar. Okay, so you're going to hit the negative button and then the log button, and then you'll enter in 2.5 times 10 to the negative 8. Now remember, you can estimate, you're going to be somewhere around a pH of 8. And when you work this out, indeed, you get something kind of close to 8. You get 7.6. So that's pretty close to 8. And that's considered not hugely high, but higher, of course, than 2.1. So comparatively, this one's more acidic than this one. It's possible to go in the other direction. So it's possible to calculate the hydrogen ion concentration from the pH. And the way that you would do that is you would, so given the pH, you would just take 10, because that logarithmic button that you're using is log base 10. So you would take 10 and raise it to the negative pH. So for example, I might want to know what the concentration of hydrogen ions is in Drano if it's got a pH of 13.5. And so we know, of course, because it's got such a high pH, it's a really high pH, that's probably going to have a pretty low concentration of hydrogen ions. So you would just take 10 and you would raise it to the negative 13.5, and that gives you about 3.2 times 10 to the negative 14. And then, of course, because it's a concentration of hydrogen ions, you have to put molar after it. And I hope you notice that pH doesn't have a unit on it. So when you report a pH, it's just a number. But, of course, this is the concentration of hydrogen ions that we're reporting here. So you would need to put molar on it. And notice that this and this are pretty close to each other. So there's this scale called the pH scale, and this is a range of numbers that you might get for pH. So pH in general goes from 0 up to 14, and from 0 to just before you get to 7, so 6.9, I guess, would be considered your acids. And then anything above 7, so from about 7.1 up to 14, these are your bases. And then right in the middle at 7, this is neutral. So anything that has a pH of exactly 7 is considered neutral, which means it's equal part, it's either not an acid or a base at all, or it's equal acid, equal base. Like water, for example, is a neutral substance. I would say most things that you put on your body, like lotions, cosmetics, those things are around a pH of 7, because you don't want to put things on your body that are really acidic or basic, because they'll irritate your skin. So just remember that the further you get, so as you go down the scale from 14 to 0, you are going from a low concentration of hydrogen ions to a high concentration of hydrogen ions. So things with pHs close to 0 have a lot of hydrogen ion, and things that are closer to 14 have a lower concentration of hydrogen ion. Also, those things tend to have a high concentration of hydroxide, because, you know, bases tend to free up hydroxide in one way or another. So we might want to discuss at this point water, because I just mentioned that water is neutral. So how is it that water is neutral? So you might remember this from the last video. This is an equation for the auto-ionization of water. And really all that means is that water molecules can ionize each other. So one water molecule can take the hydrogen from another and become hydronium, and then of course that leaves behind an OH, which is hydroxide. You can actually make this reaction, you can simplify it. So you've got liquid water, and it can either give up a hydrogen or it can lose a hydrogen and become either hydrogen or hydroxide. Now, regardless of which one of these equations you use, they're pretty much exactly the same. You'll notice that water gives up equal parts acid and base, which means that it's both acidic and basic. So mathematically, so it's equal parts acid, right? And equal parts base. Now mathematically, this works really well because, you know, if we wanted to write the equilibrium expression for water, so remember Kw is the equilibrium constant for water. You would write hydrogen ion concentration times hydroxide ion concentration. Now, from a lot of experiments, we as chemists know that the Kw for water at 25 degrees Celsius is 1 times 10 to the negative 14. We know this. This is like a measured thing. We know it. So the hydrogen, sorry, I was stumbling on my words. That would mean that the concentration of hydrogen and hydroxide are equal to each other and multiplied by each other would have to be 1 times 10 to the negative 14. So, if I took the square root of 1 times 10 to the negative 14, what that means is that your hydrogen ion concentration and your hydroxide ion concentration, if they're equal, then each one equals 1 times 10 to the negative 7. The pH, so if I take the negative log of 1 times 10 to the negative 7, gives me 7. So that's how we determined what neutral is on the pH scale. We based it off the pH of water because it's exactly half acid, half base. Water is not the only thing with a pH of 7. Lots of things have a pH of 7. It's just that water is kind of where we scale it from. All right, so let's talk about what neutralization reactions are. So you might have heard that acids can neutralize bases or that bases can neutralize acids. So what that really means is that if you mix equal parts acid, which usually contain or always give up hydrogen ions, and bases, which take on hydrogen ions and often leave behind hydroxide, if you have equal parts hydrogen to hydroxide, then of course what you're going to get is water. And we just discussed how water is a neutral substance. So you are making a neutralization reaction by basically creating water. So an example of a neutralization reaction is where you take something like hydrochloric acid, which we know is an acid. It's a very strong acid, as a matter of fact. And NaOH, which is a base, a pretty strong base. What you're going to get is essentially a double replacement reaction. So the hydrogen and the sodium are just going to switch places. So you're going to get H with the OH and sodium with the chloride. HOH you can rewrite as H2O, which is water. And then you've also created a salt. In this case, it's sodium chloride salt, but it doesn't have to be sodium chloride depending on what your acid and your base are. So all neutralization reactions will result in the formation of water and some kind of neutral salt. So, of course, you're going to be asked to determine how much of an acid or a base it would take to neutralize another acid or base, just based on stoichiometry. So, for example, I might ask you how many milliliters of a 0.5 molar hydrochloric acid solution would be needed to neutralize 2.0 milliliters of a 0.10 molar calcium hydroxide solution. So the question's asking us to figure out how much of this hydrochloric acid we would need to add to our calcium hydroxide so that all of the calcium hydroxide and the hydrochloric acid are turned into nothing but water and salt. So the first thing you're going to want to do is probably write a balanced chemical equation. So at this point, I fully expect you to be able to write an equation for a reaction given just the reactants. This is nothing but a double replacement reaction. So your hydrochloric acid and your calcium hydroxide, when they are mixed, the hydrogen and the calcium are going to switch places. So the hydrogen will end up with hydroxide to make water. So remember that H2O is really just HOH. And then the calcium will end up with the chloride, and the calcium is going to end up with 2 chlorines because calcium has a positive 2 charge and chloride has a -1 charge. So the appropriate formula for calcium chloride is CaCl2. Then you're going to need to go in and, of course, balance this equation. So we need 2 chlorides, so we'll put a 2 here. And then we have 2 hydroxides and 2 hydrogens, so we're going to end up making 2 waters. So this is your overall balanced chemical equation. The second thing we're going to do is read the question and see that we know more about our calcium hydroxide than we do about our hydrochloric acid. So because we have more information about our calcium hydroxide, we're going to go ahead and determine how many moles of that we have. And to do that, we're going to use the equation for molarity. So we know that molarity is equal to moles of solute per liters of solution. And we happen to know that the molarity of our calcium hydroxide is 0.10 molar. And we also happen to know the volume of the calcium hydroxide in milliliters, not liters. So we'll convert it to milliliters. Or sorry, 2 liters from milliliters. And then, of course, we will solve for our moles of calcium hydroxide because that's what we don't know. So when we do this, when we solve for moles of calcium hydroxide, we end up with this many moles of calcium hydroxide. Now we can just do stoichiometry. So since we know we have a balanced equation, and we know how many moles of calcium hydroxide we're putting in, we can use the mole ratio to figure out how many moles of hydrochloric acid we are neutralizing. So we'll take the moles of calcium hydroxide and our mole ratio between hydrochloric acid and calcium hydroxide. And of course, moles of calcium hydroxide would go on the bottom so that it cancels. And that will give us or tell us that we have that many moles, 0.0004 moles of hydrochloric acid that are being neutralized in this reaction. And of course, the very last thing we're going to do is it's asking for a volume of our hydrochloric acid, and it's given us a concentration. So we're going to use the molarity constant or equation and the number of moles of hydrochloric acid to determine the volume of hydrochloric acid that would contain 0.0004 moles of hydrochloric acid. So we know the concentration from the question was 0.5 molar hydrochloric acid. And we know that we have this many moles of hydrochloric acid in that concentration. And what we don't know is the volume. So if we solve for the volume, we get 0.0008 liters of hydrochloric acid. Okay, so we're almost done. The last thing we need to do is we need to convert that to milliliters. So to do that, we, just take the 0.0008 liters of hydrochloric acid, and a liter is equal to 1,000 milliliters, and that ends up being 0.8 milliliters. So if I want to neutralize this calcium hydroxide at this concentration and this volume with this concentration of hydrochloric acid, I would need to measure out 0.8 milliliters, pour it into this solution, and I should end up with nothing but water and calcium chloride and none of these two things left over.